All right, beautiful. Lovely to see you all. And welcome to Lecture 13 on Relations and Expressive Adequacy. So, what we've really got today is I've divvied it up into three sections. It's really two sections with a big long run up to the second part. So, we have section one where I want to talk to you about the properties of relations. And this is kind of similar to the lecture we had back in lecture 8, where I gave you some really basic set theory stuff, if you remember those lectures a long time ago. Right? What I want to do for section 1 here today is present you some notions and things that you'll see. And people you probably have already come across some of these before. You're certainly going to see them as you move forward in your studies. So the aim isn't really to give you like a massive, deep appreciation of the mathematical understandings of relations, but just to get you to think a little bit about the concept or the properties relations can have and how we might kind of model or map them. So that's what we're going to do for the first section. And then we have this second section, which is 2 and 3. And here, really the aim is to do a little bit of meta logic. And that's to think a bit about the sort of logical systems we could have developed. So, of course, I taught you TFL and I taught you FOL. But what we're going to try and talk about today is how we could have maybe done this differently. How you might approach thinking of, in particular, TFL in a radically different way. It's worth noting, and just to stress, the stuff in section 1, that's the only stuff that isn't supplementary, i.e. only the material in section 1 will there be any kind of questions on any exams or anything like this. There's a couple questions on the homework about these two sections, but it's really just to kind of, hey, think about it a little bit. It isn't going to be any kind of exam questions or anything like that. So what we'll do structure-wise, we'll talk through the first section, we'll take our break, and then we'll come back and just kind of go through the whole meta-logic spiel all in one big run. And again, the meta-logic stuff is something that's interesting. I think it's worth thinking about. It's worth you knowing. But I also don't think it's necessarily something you need to know in order for an exam. So that's the plan. Let's go ahead and start. We'll start talking about properties of relations. An important thing here is obviously, right, we haven't really dealt with relations in this kind of extensional way as we did with interpretations for a long time, right? The last time we really kind of got into that was something like week 6 or 7. But when we think about relations, these multi-space properties, well, there's some interesting things about them. First is we can talk about the arity of a relation. And the arity of a relation is effectively how many gaps does it have? So the easy one is a binary relation, right? This is one that has 2 places. And in fact, almost everything that we've dealt with has been binary relations. But you could also have 3-place relations, is in between, or really any n place, right? You could have as many spots in a relation as you like. One of the reasons we just simply haven't done these sorts of things is really if you get how to play around with binary relations, the rest just kind of continue onwards. And as well as thinking about the arity of a relation, that is how many gaps does it have, we can talk about the kind of converse of a relation. So the converse of a relation is, put really loosely, the kind of opposite. So thinking of it in terms of an example, the converse of the is taller than relation is shorter than. Put more in kind of a formal way, we can say that some relation R star is the converse of relation R if and only if X R's Y, then Y R star's X. So, right, if it holds in one direction, then the opposite, the converse, has to hold in the other direction. Again, easy way to think about it. If Nathan's taller than Mira, then Mira is shorter than Nathan. And there's an interesting philosophical and mathematical question here about whether we should think that really relations and their converses are different relations. Because strictly speaking, we could understand them as the same ordered pairs, just sort of flipped around. But there's good philosophical reasons for thinking that they need to be distinct. It's something to kind of think about. Again, not really something we're going to talk about, but this is useful terminology. Because you'll occasionally see this kind of thing being thrown around in like linear algebra, where you need to talk about the converse of the relation you've been given. Now you know what the hell that means. Right? If you've got a relation, the converse is just flipping the order around. Right? It is the relation in reverse, as it were. And I should say, I'm going to throw a lot of terminology at you. Right? So I'm going to give you a ton of definitions. There's going to be 3 really big ones to remember, and we'll flag those up. But there's a bunch of other terminology here that you'll come across occasionally, and it's just really worthwhile knowing what they are. So that's really the kind of purpose today. So here's our first thing. Right? When we think about the properties of a relation can stand in different ways, right? It might just be distributed kind of randomly, or it might have certain very specific mathematical features. So here's a really simple one. A relation might be reflexive. And we'll say that a relation R is reflexive if and only if everything stands in the relation to itself. So if we're thinking about this in terms of our diagrammatic interpretations, if you remember those from way back when, right? A relation's reflexive if every node has a loop. So maybe interestingly, have you come across this notion? Seen anything talking about like the relation that we're thinking about in the model is reflexive? Blank faces, so I'm taking that as no. Right? So again, reflexive means that everything in the set, or every node in your graph, or every object in your domain stands in the relation to itself. An easy example is the same height as. Everything is the same height as itself, even things that don't have a physical aspect. We know. So again, reflexive relations, it's the loop. Everything has to have the loop. And then you can start to think about kind of ways of weakening or modifying a relation, right? So we might have, okay, relation's reflexive. Or perhaps it's irreflexive. That is, everything in the domain does not stand in the relation to itself. And note the scope of our negation here. It's that everything does not stand in the relation. So nothing bears the relation to itself. Easy example is older than. Nothing can be older than itself. Contrast irreflexivity with what's often called areflexive or non-reflexive relations. And that's just when both of these fail. So the idea here would be there's at least some loops, but not everything loops. Bad, sort of slightly sad examples. Hates or loves are good cases because, for better or for worse, some people love themselves, some people hate themselves, but not everybody does. And it's worth noting, this is a kind of weird terminological minefield. You will sometimes see people use areflective when they mean this, or areflexive to mean that. But again, the important thing here is to just kind of see the conceptual notions, right? Reflexive means everything loops. Irreflexive, nothing loops. Areflexive or non-reflexive means some do and some don't. So this is the first kind of property. And this first one of reflexivity, that's one it's worth remembering. Again, it means that everything in the domain stands in the relation to itself. So that's our first kind of feature of relations, right? Reflexivity. The second one we'll talk about. Yes, please.
So let's say for like if a domain has only one object, like one name. So would any R would be reflexive?
So not if the thing doesn't stand in the relation to itself, right? Because it could be that the relation's empty. Remember, that was a way we could construct the extensions of predicates. So the domain has one object in it, but the extension of the relation could be empty. In that case, it wouldn't be reflexive because there isn't even anything that stands in the relation. But it would be irreflexive, kind of on the cheap, because the only thing in the domain does not stand in the relation to itself. Make sense? Yeah. So good. The thing to remember here is what we're really thinking of is the extension of these relevant relations in comparison to the domain. So for the relation to be reflexive, right, every single object in the domain also needs to be in the extension of the relation relative to itself. So the ordered pairs that make up the extension of R need to be the one object, the one object. That'd be the way. Okay. So there's our first property. Please. Good. Yeah, so remember, when we're talking about relations, we're thinking of relational predicates, right? So if we remember, we had non-relational predicates. These were the one-place ones, so F and G. And relational predicates are the ones that had more than one spot. In fact, interestingly, to go back a slide, I mentioned we can talk about the arity, right? And we marked a difference between properties and relations. But really, properties are just one-place relations. They're all the same kind of thing. Just properties only have one space. Is a dog has one space. Is taller than has two. Is in between has at least three. But they're all still roughly predicates, and we can still understand them extensionally. Okay, so again, our first one, reflexivity, and then its kind of modifications. Our second big property is symmetry. And symmetry is, as the name suggests, it just means if it goes one direction, it goes the other as well. Or more formally, relation R is symmetric if and only if for any x and any y. If Rxy, then Ryx. So if the arrow goes out one way, it also goes immediately back. Every arrow is double-headed. An easy example is a sibling of. Is a sibling of is a symmetric relation. If A is a sibling of B, then B has to be a sibling of A. So, symmetry, again, if the arrow goes out, it also comes back. Asymmetry is a one modification. Asymmetric relations are ones where, well, symmetry fails. This could be because there are no arrows, or there's only one arrow going one direction, however you like. But importantly, it just means that symmetry fails. Easy examples, loves and hates. For better or for worse, right? Unfortunately, love is not always reciprocated. Thank God, because otherwise we'd have a lot less music, right? But hey, there we go, right? There's an asymmetric relation. It's just one where sometimes there's at least a case where arrow goes out and it does not come back. Contrast that with what we might call an anti-symmetric relation. So this is notable and it's different, right? An anti-symmetric relation is one where if the relation holds in a symmetric way, you actually just have identity. So if you have, right, for all x and all y, if both cases go, if the arrow is symmetric, then it turns out you didn't have two objects after all, you only had one with two names. An interesting case here is a part of. So we won't talk about it, we'll mention it next week, but there's a logic of mereology, the logic of parts and wholes, and it defines parthood as an anti-symmetric relation. If A is a part of B and B is also a part of A, then they must be the exact same thing. And it's worth noting some relations are neither symmetric nor anti-symmetric. Right? At least as old as is one that's neither of these. Neither symmetric nor anti-symmetric. Okay. So, again, the important property here, please.
If something is neither symmetric nor asymmetric, doesn't mean it is asymmetric.
Good, yeah. Basically. It's important to see what I'm trying to get at here is the difference in this sort of structure. That's all. So you could still have a relation that's like letting you down with 2 out of the 3, but then you still get the third one. That's perfectly fine. So again, our second property here, our second big one, is symmetry. Reflexivity was everything has a loop. Symmetry is if the arrow goes one direction, then it's got to come back as well. Our third big property is transitivity. And transitivity is probably a notion you've heard before in other contexts. If you've done algebra, it's something like that, right? So we'll say a relation R is transitive in the relevant sense if and only if for all 3 objects, x, y, and z, if x r's y and y r's z, then x r's z. Easier to see it this way. If 1 connects to 2 and 2 connects to 3, then 1 connects to 3. There's an arrow that goes from your starting point to your third option. Causation is plausibly transitive. Another easier one is taller than, is very clearly transitive. If Nathan is taller than Amanda, and Amanda's taller than Mira, then Nathan has to be taller than Mira. Again, the idea with transitivity is if you have a kind of daisy chain from 1 to 2 and from 2 to 3, then you're also going to have a looping arrow, a long arrow from 1 to 3. So transitivity is a useful notion. Note that it can be combined with these other ones, but of course it is still technically a different property. And much like with the others, we can play around with it. We can talk about a relation being intransitive. So we can say a relation R is intransitive if and only if it fails. Transitivity is not the case. Easy example, I quite enjoy this as an example. Eats is a good one. If A eats B and B eats C, that doesn't mean that A eats C. Just let some time for digestion go through and you'll figure it out. But you can also go something even stronger, right? We can talk about a relation being anti-transitive. Because this just allows for some instances of transitivity. It just says it's not always the case. But you might want to go stronger. You might want to have a relation that's anti-transitive. That means if x r's y and y r's z, then you cannot have x r'ing z. A silly example, but my favorite, defeats in rock, paper, scissors. Rock beats paper, paper beats scissors, but rock definitely better not beat scissors. Other way around, that's fine. That's fine. Okay. The important thing again with these 3, if we think about transitivity, it just means again that you kind of pass the movement along, but you can get directly from your first to your third. These other weakenings are just ways to kind of define relations, either just that it fails or that it's guaranteed to not be the case. It cannot have the third loop. So it mentioned already that while we're talking about these properties as different features, right? Reflexivity, symmetry, transitivity, you can have combinations. So you can have relations that are reflexive and symmetric, or reflexive and transitive, right? Or you can have what we'll call an equivalence relation. And an equivalence relation is one that's reflexive, symmetric, and transitive. It has all 3 features. And equivalence relations are incredibly useful in philosophy, but also in mathematics more generally. A really paradigm example of an equivalence relation is numerical identity. Everything is identical to itself. If A is identical to B, then B is identical to A. And if A is identical to B and B is identical to C, then by God, A better be fucking equal to C. Another easy one, indiscernibility. If A has all the same properties as B, and so on, you can figure it out. Equivalence relations are, if you like, the gold standard. But you can also have slightly weaker ones. We can have this kind of fun one, which is a Euclidean relation. So we'll say R is Euclidean if and only if for every x, y, and z. If Rxy and Rxz, then Ryz. So notably, this is slightly different than transitivity because this is, right, if 1 gets you to 2 and 1 gets you to 3, then 2 must also be connected to 3. So it's giving you a different way to kind of complete the triangle. And it's called Euclidean for silly little reasons about Euclid's geometry. But it's just another feature, and it highlights again ways that you might think about kind of properties of relations. So the three that are important for us, again, reflexivity, symmetry, transitivity. Those are the three that matter. And you can combine them if you want to get an equivalence relation. Now, interestingly, one thing we can do is if we have a relation that fails to be reflexive, symmetric, or transitive, we can define a closely related cousin that will be the relation's either reflective, symmetric, or transitive closure. And if you've done some mathematics, you've probably seen something like this notion in play. So what we do, if you have a relation that isn't reflexive, say, is you take its extension. So say I've got Alf, Bart, and Charlie, and its original extension for the relation I'm interested in is Alf and Bart, Bart and Charlie, Alf and Charlie. So note that this relation is not reflexive, but we can build the reflexive closure by taking that extension and adding whatever ordered pairs would be required to make it reflexive. So you can kind of think about this as maybe like, hey, this is the is taller than relation, and the reflexive closure would be is taller than or the same height as. And now what that does is it gives you a close relation that captures what was already there, but also lets you then kind of round off the whole collection. So the reflexive closure, you just simply add whatever extensions you need in order to then have the relation be reflexive. And note, we can do the exact same thing with symmetric. We could take this relation and get the symmetric closure. What would we need to add to get the symmetric closure on this extension? So we've got A to B and B to C and A to C. If we want the symmetric closure, we then have to add the relevant extensions that give us the order in the opposite direction. So we need to add B to A, C to B, and C to A into the extension of the relation, and then we would have the closure, the symmetric closure in this case. And finally, we can ask, what would we need to add, or do we need to add anything to get the transitive closure? This relation we've defined, is it transitive already? Yeah, right? Because for every x, y, and z, if Rxy and Ryz, then xrz. And that's the only collection where everything works out fine. This already is transitive, so the transitive closure would just simply be what we already have. So this is something that you'll start to see. You'll start to see this occasionally with people talking about going over data sets, turning data sets into their relevant closed data sets. What they're doing is making them more digestible by basically performing one of these operations. Even if the initial kind of relation you're looking at or function you're looking at isn't reflexive, symmetric, or transitive, you can quickly turn it into one by just adding the relevant data points. So this is the kind of reason why I wanted to talk about it, because again, it's something you're going to start seeing. People will talk about these closure relations, and I want you at least to be vaguely familiar about what the hell they're doing. Okay. The last real big thing I wanted to mention in this section is to talk about a notion that you can get using these features. And this is the idea of a partial ordering. Interestingly, have people seen this notion when you're talking about data? Because this is something I wouldn't be surprised if you have already come across. So a partial ordering, as much as the name suggests, it's going to give you some foundation and then a structure that builds from there, an order that kind of ascends from there. So a relation R is a partial order relation if and only if it's reflexive, anti-symmetric, and transitive. So for every x, it's going to be such that it stands in relation to itself. For any two, if they stand in relation to themselves, they're identical. And then you get, right, if x bears it to y and y to z, then x to z. So what you end up with on a partial ordering is a collection of entities, or whatever you want to talk about, that will be at a base level. And then everything else can kind of ascend from there. Explanation is plausibly a partial ordering relation. There'll be some facts that you just simply take as given that don't have explanations, and then they go on and explain other things. One relation I'm very interested in is grounding, which is a kind of metaphysical explanation. Grounding is taken to be a partial ordering. A successor function can be understood as something like a partial ordering. You have some base unit, and then you define successors as things that are kind of coming along later. So again, this is a kind of notion that you'll run across every once in a while, especially if you're dealing with highly mathematized data sets. And I suspect you might not have anyone at any point tell you what the hell it means. So I wanted to take 2 minutes and just to tell you. So again, the kind of important things for our purposes, thinking about relations being reflexive, they loop. Symmetric, if it goes out, it comes back. And transitive, if 1 to 2 and 2 to 3, then 1 to 3. And then different ways we can start to kind of plug these in together to get different kinds of features of relations. So there's a bunch of mathematics and a bunch of philosophy that hinges on what we just talked about. Most of it's well outside of our ballpark, but these are concepts you're just going to come across later on. And again, much like with the set theory, I want you to at least be like, oh fuck, Nathan told me what that was. Right? So at least you'll have some inkling of what these concepts are. Okay. That's really all I wanted to do with regards to the relations. So before we take a quick break, I want to mention the kinds of questions I'm going to ask. I don't know if people have had a chance to look at the worksheet yet. I doubt it because I put it up last night. What I'll ask you to be able to do is to take a kind of relation set, so some graphs, little dots with arrows, and add arrows to the relation, add arrows to the graph that will make the relation reflexive or symmetric or transitive. And similarly, to say things like, okay, is this relation already reflexive? Is this relation already transitive? So identify from either diagrams or extensions whether a relation fits the feature. we'll talk a little bit about that on Thursday and Friday in the tutorials. We'll go through the worksheet. We'll also, of course, do some more FOL natural deduction to make sure that everybody's kind of up to speed with that. But the plan now, so it's 1:18. We're going to take a 12-minute break, and we come back. We're going to talk about the metalogic stuff. And I want to stress what we're going to talk about after this. It's entirely supplemental, so I won't feel offended if you guys don't come back. But I do want to tell you this next stuff's really fun, but it's not on the exam, so I won't feel bad if you don't show up. But anyway, okay. So we'll take 12 minutes, come back, and we'll go from there.